Welcome to Tutorial 10, your first practice with recursion. Now, all code solutions for this tutorial can be found in the tutorial class library. So home/library/comp1633 tutorials tutorial 10. So before continuing with this video, I suggest you go and copy that code into your main directory so you can follow along and play with this code. When you copy that directory, you will find they have multiple files in here because once again, to get more practice with separate compilation, you have the same make file that I've been using from beforehand where it makes it easy to say what you want to target, just listing out all sources that you need, and then everything else gets handled for you. And for right now, because this is tutorials, I have it clearing the screen and running it every time to compile. Just if you're doing that continuously, I like to do that just for right now when building, but also providing cases where you can clean everything and just do a complete build of what you need. For files itself, you will find the ioutil.h and .cpp. These are the ones that have been presented in previous tutorials, just allow for some methods for common input and output that's used in the actual main. You have the tutorial 10 main, where this time I have actually set up a makeshift menu. So may not be perfect, but you will see that it contains a basic choosing menu using the ioutil. So reading the choice from the actual user, using the ioutil method, validating the actual input, and then running each individual choice, where I've got all the coded questions that are not tracing in here as individual functions that are then called later in the actual program itself. The list.h and list.cpp contain any methods that are recursive but that relate to linked lists. And then the rec.h and rec.cpp contain methods that are just purely recursional but don't do anything with linked lists. Just to kind of keep separating the code and seeing how you can break up your program into multiple files for organization and keeping doing your work. Okay, so for question 1, we'll be going through just doing a trace of the n factorial method with recursion. And realize, again, recursion is just a function calling itself. But what's important is to understand what's happening under the actual scenes for the machine. So just like you would have been learning with linked lists and everything, the idea that you have memory and visualizations, you have to remember that you have a system stack that keeps track of all your calls to your actual functions. And this is where your local variables for all your functions are actually stored, so ones you're not allocating. So if I was to somewhat draw this out, I won't do it perfectly, but you know, when we think of a stack, you want to think of things like a stack of dishes that keep stacking up, that go up on top, that you have like here the bottom, and then here you have the top right here, and it just keeps growing upwards like that. So the idea is that when you call functions, you make any function call in your actual program, the system will first make space for the parameters that are being passed into it, and also then any local variables within that function. And that's called like a actual function or stack frame. So if you call anything, so in the very beginning, you would have your main. That's going to be first here. So all of your local variables will be stored in here and everything you're doing your work. When you start then calling functions from actually main, this will then execute that the system will make a new stack frame for that function that you're actually calling. So whatever name you have, you're giving a name, it goes there, it knows about the local variables, it creates calls to that. So you have function 1. Then if function 1 calls another function and is not done executing, then function 2 is put onto the stack. And this keeps growing up for every single actual function call, so growing up this way. When a function finishes, that stack frame is cleaned up, and we return back down to the previous one. And this is where the memory is, and it keeps track of, again, where the code is and what line you're actually at. And so it's more, the stack here, remember, is just for your variables and your memory. There's other stuff that's keeping track of where in the program you have that it's calling. So when you're looking at recursive functions, what you have to realize, like the one we have here for Factorial, is we have our original function right there. That we are like, that's the definition, the prototype we're having it. And in here, it seems weird that you're like, well, how in a function itself can it call itself? Well, the fact of the system is when it's calling a function, it just goes and creates that stack frame. So for any local variables. So things like this int n that we have here and whatever else it needs to deal with, even though the results pass by reference, but you have those local variables you're working with, and it'll make space on here. And so say a first call to Factorial, we'll put it onto the stack. And then when it comes down to here and hits this line where call itself, well, another call will be putting onto the stack. And then the idea is it kind of restarts. You think, okay, it's here back at the start again, and it'll keep going. It hits here, okay, it'll put another one on the stack. And the idea is that when it finally reaches the bottom here and hits the return, or the end of the function is, we'll exit from here, and we will come back to the previous function, and we'll come back to where that call happened, just like you had functions before. So when you're returning from a recursive call, you come back to the line where you had that recursive call right there, and keeping track of everything. And so this is the stack and why you can have recursion that works. So when we need here for this problem is actually trace it out. What if we did a call to our factorial? So I'm just going to go F, just so I don't have to keep writing out factorial the entire time. But if we did F, and we have the N, and we know R, and here let's start that N equals 4. So we're going to start tracing where we have 4, and we've passed in actually the R value right there. So to do this, I want to first just start keeping track of everything. So we know we have R being passed in, it's passed by reference. So over here, I am going to just put R, and I will just keep putting the actual values that I get here. That starts with. So we'll assume that R starts at, say, 0. Whatever, we don't know what's coming in. We'll just assume it starts with 0, and I'll scratch that as we go. So what we're going to start is I want to start drawing out each function call to make it easier to keep track, to visualize kind of what's happening on that system stack. So we got 4. Keep passing the R here. So this is the very first call. So now what I'm going to do is also right now keep track of a dot of where we're at as we go stepping through this code for these functions. So for this first call, it comes in here. We come down and we hit this line, and N here. Is it equal to 0? Well, no, N is equal to 4, so it doesn't go into the if, so it jumps down here to the actual else, and we come down into the else, into the actual function itself. So we're calling it. So from here, we go down to the next line, go right here, and now this is a recursive call. So we have to here is like, okay, this current function is going to stop, and it's knowing from right here that's calling, and there's going to be a new call that's made to the function. So we get a new stack frame that's put on. So I'll draw that as an arrow. Get a new call to the actual function right here. And so this first function you have at the top here is not done running yet. It's still there, and it's going to wait for the next call. And this is the next call that's actually happening. So right here, this says that it's N minus 1 is what's being passed in. N right now is 4. So we get 3 passed into here and result put in. So that's one function. Now the idea here is that for this new function that we're working with over here of F, we're passing in 3. It's like a brand new call. So it's going to start at the top. So I'm still just going to keep track that we know, okay, for F, it's still returning from that line right there. So when we come back to this function right here, it's going to be coming back to that actual line with whatever's returned. Whereas for this F we have down here, let me actually switch the pen color. This new F, I'll even put the F as green right here, is starting at this first line right there. Ooh, and I just realized while copying this, I forgot to copy one piece of code. Sorry. I think you're getting used to me screwing up at this point in time. But that's okay. Life happens. We all screw up and we just keep moving forwards for the next step. Learning moment. Oh, come on. I can know how to use paste right now. Whatever. I'll just type it. Forgot that line. That's from the code. That's what happens here. So again, mark it right here. This is the blue. We're in F. It starts here in this line. We come down to here. Is N actually 0? Nope. N is 3. So it skips down to this line, which will kick in a new recursive call again. Here are. And so again, this F that's up here, we actually are not done there from yet, and so it's when it comes back, it's also going to return and come back to that line. But we have this new call that we're doing down here, and we have n minus 1, n is 3, so we get 2 this time. So it seems weird, keeps track of this, but this is where the system stack is keeping track of everything from right here. So I'm going to speed up because it's going to go about similar on. Now we still haven't hit that base case that stops. As long as we keep having this recursive call, it will keep going through all of those actual steps. So we get f, okay, this f is here, starts base case, is n equal to 0? Nope, goes to the actual recursive call. So n was 2 here, it's n minus 1, so we're getting 1. And the idea here is, again, f is still coming back to that line when it returns to continue on. F, same thing here. We start with this one down here, bottom of f of 1. We get here. N is not actually 1, so it's 0, so it's going to come down and do this recursive call. Right here, and this function will return back to this line. So all these, when they return going back up this chain, when we're done doing the recursion, will all come back to the line where I had the recursive call. So I've got all these arrows pointing back here to keep track of it, even though this looks messy. So we hit this last call, we get 0. Hey, look, n is 0, so we will not be going to the else, so we will not be going to recursive step. We'll be hitting our base case, which will just actually set result to 1. And so again, this is passed by reference, that's why I'm keeping just one variable over here. So I've tracked it out from here. This then goes down to the actual return and exits. So it means this function will finish. So it'll be done, and this is like that stack frame I drew earlier, is going to go back up to this previous function. Now it is going to continue on from that line from where it started from, so right here. So we're going to come back, and it's going to go from right here down to the next line below this. And we know, as I'm keeping track of, okay, right here, that's n. Like 1 is actually n. So we come back, we're continue on. Now it's going result times equals what is n. So n here is 1, so that's 1 times by 1 equals 1. Magical. So I'm going to say, well, okay, we've had 0, that's crossed out. Then we had 1, that's crossed out. The next change is actually 1 for what r is. That's going to then continue on to the return. So the bottom function here will exit. It'll return back the function that was above it. That's this one here. And that function will return back from where that call was. So again, we have the same steps. It's going to leave from here, go down to here. Remembering that now here, n, that was for this function, is 2. Right here. So now we're getting a result times equals 2. So that's 1 times by 2 equals 2. Yeah, well, I'll just keep it on track the way I was doing it before. Scratch out the 1 that we had. Boom. Now the new answer is it's 2. Same steps from here. This then goes to the return, so this bottom function will finish. We'll return back to the one that's above it. Here that has this 3, so same thing as every time that we've done before. It's going to be returning from this spot right here. N was 3, so going down then below here. And so then we have the 2 times by 3 equals 6. Boom. And finally this function finishes. We go up to the top one and it will return here, and this time n is 4 for that function. Returns down from right here. So you get 4 times by 6 equals 24. Boom. And then this final function will finish and it goes back to whatever called it before this. So the important thing is to understand where you're returning from, so keeping track of that, the idea of these visualizations to see what's happening, but also be really clear of what happens when you do work before the actual recursive call versus what you do after. Because any work that you do before happens as you're going down on these recursive calls that you're going here. So as you go up, you hit the base case and then it returns back up to here, is that this code right here, that's above A, happens here. So in the way that you're going down, so you're making the recursive calls. This code that's after only happens when you're returning back from all the actual recursive calls. So these are tools that are useful to have when you're starting to design and build other actual functions. Okay, let's return back to the actual rest of the tutorial. So all the code is here, and I'm going to go through some of these, and others I'd like you to step forwards to actually run and make everything else. So next, we're supposed to write a recursive power function which receives a base and an exponent and returns the value of the base raised to the exponent. It is guaranteed the exponent will be non-negative. So we have to write this as a recursive function. Now, important for this is just to realize, okay, well, what will the base case be? Like we have to know what the recursive case will be. Like how do we shrink the problem to one step down, going smaller from right here? And then we also have to know, okay, well, when do we actually stop here? Like when do we actually start doing that? So if we flip back just quickly just to go into our design, if we are trying to do a power function from right here again, so we've got P from power, we've got B to represent base, and we've got E to represent the actual exponent. What we're supposed to be returning from this is basically B raised to the power of E, right there. So even if I just take an example, let's say that is 2 to the 3, right here. Now, equivalent way to actually write this is that's the same as just 2 times by 2 times by 2, right here. And so you get the exponent like 1, 1, 1. These are the actual same things. So we know like the base will always keep going down, but then the idea is, well, okay, well, what's happening with the actual exponents right here? We could also write this as, well, 2 to the third is the same as 2 times by 2 to the fourth from right here. That's the same. If we try working it out, so again, I'll just do this. 2 times by 2 times by 2, that equals 8 right here. Now if we have 2 to the third is equal to 2 times by 2 squared, that equals 2 times by 4, so that equals 8. So we are getting the right answer. We're seeing that shrinks down. So we know so far that we can say 2 to the 3 is equal to 2 times by 2 to the 2, which would also then equal 2 times by 2 times by 2 to the 1. And so what we can notice is our exponents are going down each time. And that's one way we can deal with the recursive step from right here, and we can stop when we start actually getting to actually 1. And we know each time it's then just going to be the base times by the results of whatever comes afterwards for this. So we'll switch back to here and let's open up the actual code so we can take a look at it. This function that we're dealing with this is in actually the rec.cpp file. Boom, window management. So we can get down to here and you can see a similar thing. So if we get down to the results for the actual power and shrinking down here, we can see the exponent. We have a base case of here when we hit 0, just return actually 1. That's the result. Any base raised to actual 0 is supposed to be 1. Else, what you have a result is your base times by, then your recursive call. And so in this case, this is our recursive step of minusing 1 from the exponent that we just saw before. So again, this is important for the base to stop doing the recursion, so the base case, and then this is then the actual recursive steps. And what you're realizing is right here is even though I said that before and after, the result equals base times, remember this will not be run till after this function is actually called. So it's executed. So these calls will go here and it'll keep having that continual recursive steps of more actual having the stack activation frames going all the way actually up right here, and you'll get when you hit the base case, and it'll start returning back down, and then it'll come down doing the actual times and continually putting the results back for us. So if we want to run this, first we'll compile it. Do here. And just to make it clear, too, this is the actual main right here. And so for calling this, again, I've just set up a basic menu to do easy choices with pausing between everything else so that I can just compile and run this once and show each example and you guys can play with it. And so this is question 2. And so question 2, it just first uses that IOUtil just to read in an int for the base and an int for the exponent. And if there was nothing wrong with the actual inputting the data, then it will actually output the actual result doing the first call to our power function. Okay. Here base, so we'll go 2. We'll do our exponent 3. Yay, 8. How entertaining, eh? 2, keep doing even the same thing. 2 to the 16. There we go. 65,536. Okay, it's a power function. So let's move on to question 3 now. So this one's a little bit further. This is another algorithm, so I'm just going to more demo showing this run and explain the code than explaining how to break stuff down. This should be more practice for you for writing the recursive method, so I do suggest, even though I've posted a solution, you have this code, go back to understanding A, the algorithm for this, and B, okay, well, how would I actually write this myself? So question 3 is, write a recursive function to display a decimal integer, so base 10, as a binary notation. You should remember this general algorithm from your comp 1631 if you did it. If not, the algorithm's there and you can look. And so this is the kind of repeated division method as you're going down to show this. So given the n, it will actually just show the actual binary number for you. And so the code that I've provided here has the actual comments from the solution. So the algorithm is, if just a single binary digit, you just need to print it. Otherwise, print the rest of the digits first and print the current digit afterwards. And we're just doing the recursive case of dividing. So this is where you're dividing by 2 every time when you're getting the number, getting the result, and continuing on with the actual remainder that you're working with. So you can see our base case here, that if we hit that our n is less than 2, which would just be 1 digit anyway in binary, 0 or 1. So, 0 remains nothing, 1 remains this 2 from right here. So that's what you'd have. So anything greater than 2, you need more than 1 digit to deal with binary. So we're just outputting it. Otherwise, we're seeing here we keep doing the division by actual 2, and then once we're coming back, so this goes all the way down, working its way, so that we can end up going down as we come back, we'll be printing the first digit, then the second digit, then the third, then the fourth, and the fifth. For the work here, it just comes back and uses the mod operator just to print out the remainder from 2 as we're actually doing this work. So continually breaking this down. And so kind of doing a recursive step till we get to the first bit, and then going all the way back up for everything else that we're working on. And so this case, the dividing by actual 2. If we come back and run this here, we still have the same running program. You can just select 3 for question 3 for the binary from right here, and we can start working with everything else we expect. Let's just do 0. Ooh. Oh, yeah. My own program, because it's positive right now, actually said 0 will not be counted for that. Right here, let's just do 1. Result is 1. Not so entertaining. Let's do our actual 8 from right here. So 1, 0, 0. Fine. And let's say do 2, 5, 5. Boom. So you can validate this yourself, but you can see the steps as you go through. And I do suggest, if you're not sure how it works, take and draw it out in the board. So draw the steps of what's happening when things are being executed. Okay. Next question is, use the following node structure. So the one that we've seen before to deal with this, to actually define working with linked lists. So write a recursive function to find the length of a linked list. So the base case here. What list is easily identifiable and known as a length? So that's your small base case recursive, thinking where we're doing this. Now, one thing to think about is, first off, if you're not sure how you're doing this, how would you even figure out the length at all? So how would we get the length at all when we're working with any kind of code with linked lists? So if you want to follow along and even see the solution, I'm going to write something else here so you can just see how would we do this loops versus if we were doing this with recursion. we just want to open up list.cpp right here. It has the same create demo list that you've seen before. It has the delete there as well, and we've got our usual write. But here we've got the recursive case for the length. But let's just say, for right now, because I want to at least code something live. Yeah, stop copying and pasting things, kidney. Okay. Let's just say we're going to make our list length. Let's call this version 2 right here, which will just return back it as a list. So if we're going through this and doing it with a loop. First, you'd expect we'd have to have some kind of count to keep track of how many nodes we've actually seen. We're going to make sure that we need a moving kind of reference that starts at the beginning of the list. And we want to move through the entire list, making sure we see every single node. So we want to let it go through the entire list until it falls off the actual end. So hitting null right there. And then to move it forwards, to make sure that our reference is moving through every part of the list, we do our step of moving the reference forward. Now that is, so it's your general one of starting at the list, going through all of it, using a while loop just in case the list is empty so that we skip over everything else. And you have this where we're moving forwards. And the idea, if we just want to do the actual count, you would just increment your counter. Every time we see a node, just increment your count. And the idea is that by the end of the time I get out of this list, the count will be the number of nodes you've actually seen. Da, 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 da. There you go. And we would just return that count. So this is our basic getting a length. It's not the most efficient. There's better ways to actually do this, but this is one way of just like counting it as we go through each step, so starting the beginning. So we know, okay, if the list is empty, so cur would be null, so head would be null from right here. It won't go into the actual loop. It'll skip over, returns count of 0. Otherwise, this will step through every single one. So what we want to see is like, well, how does this actually compare then to the recursive version? And you want to think is, well, what's stopping all of this? So one we have to see is, when can we stop? What is the smallest list we could ever have that we'd hit? And that's at one case where we think of here being null. Like, well, if we have the head, if head was null, we wouldn't even go into this loop, we would just exit. And that's the smallest list, an empty list. That's your base case. Anything else after that, you have this case where we're going to the actual next node right here. So that's your recursive step using current arrow next. And instead we just keep up adding 1 as we go. So every time, same thing as we're adding 1 here. So when you see the recursive method that's just below, this is the recursive solution, you have the length, whatever you're going here. But we come in, have head, so if head is null, just return 0. If not, you have your length is 1, because we would have had 1 node plus if there's any more nodes after that. So we have that list arrow next, and so this is your recursive step. So this head arrow next is equivalent to the current equals current arrow next to move from right here. And remember again that the code right here of that 1 plus and the length is this will not be executed until this function finishes running. So this is all afterwards. So it'll go all the way to the end of the actual list, and this will return back 0. Then it'll add 1 for that node, and it'll keep going back all the way to the actual beginning to count up all the nodes you're actually working with. Boom. Just going to clean up the code so you can copy and know that list counting here. I'm just going to remove it now so I just keep some clean code with what we had before. And we can go and see that this is now question 4. So for question 4, I've set up a few lists so that just automatically runs. So it's the same thing as seen before, that demo list where we create a linked list with like 1, 2, 3 in it. This will create a list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then list 3 will have null. And so we should see that L1 should have a list size of 3, L2 should be 10, and L3 should be 0. And then you can see from right here that I am also making sure I delete the lists at the actual end. So we'll go into running step 4 up top, and you can see there's our list, size 3, here's our next list, size 10, and our empty list, size 0. Okay, good. Now here is, next one is to write a recursive function to print the linked list in reverse order. And here's a very interesting thing, is if we go to our linked list here, remember what happens if it's making calls before or after doing the recursive step. So here's your calls right here, and Here's your actual starting solution. Now, this one's a little bit weirder, you may see, for other stuff. What I have here is, this is the print reverse is what's being called, but I wanted to print out the same as my previous list. And so I wanted to have the opening and closing bracket afterwards. So the print rev is not actually the recursive function. What I did is then I made what I call a runner function, which is actually going to do all the recursive steps, because I just wanted to have these printing of everything here, and I also wanted to keep track of, so I can have commas at the end and where I'm at for these steps. And so I'm using an extra thing here to keep track of a count of where I am. So you can see this count here. And so the idea is then the count starts right here if at actual 0, and then it increments by 1 as we keep going. And the idea is that it goes all the way up to the line of the list, prints it off, and then we're coming down here is the very first node, which would be 0. I don't want it to actually print the actual comma. So it just prints out the commas, but we're getting the very last one. So weird either way. So we're starting the actual call off with the head of the actual linked list right here. And we're moving forwards, the same thing. We just have a base case of stop going forwards when you hit null. There's no more nodes from right here. But so if we're not null, so here you can see I don't have explicit if then else, but here we have the if is it's not null, do the work. If it is null, it won't go into the if, goes down to the else, and then actually returns here. We're doing the recursive call, but you'll see the actual print is after the recursive call. Because remember, we do not return from this until we hit the end of the list. So this will cause a whole bunch of recursive calls where it'll go all the way up, saving all that kind of like activation frames, all the way up to the very last node. And when we hit the end of the list, it'll start returning from all those functions. So it'll be coming out and then printing that actual data. So it's important that this is afterwards. Then I just have this count right here just so I can get that print. And so I'll even demo how this quickly changes. So I still have the code here. We can go up here and run number 5 right here. And you can see then here, go down just so you can see the original way I set this up. Has a list of size 10, a list of size 3. So I print it out and they should be reversed. And you can see here's the original list, here's the reverse list. Matches up to what you expect for all 3 cases right here. What I'm going to do is going to exit out of the actual program. I'm just going to change one thing right here, just one thing. I'm going to copy the cout that's after the actual recursive call. Just comment it out. And just demo the fact that if we go up, if we put it above here, if I put the print right here above, it'll print the nodes as we're going, because it's going to come in, print the node, then do the call. And then it's going to come in. So we're going to return from here, which will just exit out afterwards within these cases. This is just a quick thing. So if I go remake this right here, and now on step 5, ignore the commas, I don't care, but you can see, hey look, it's 1, 2, and 3. 1, 2, 3, 4, 10. And look, we solve the issue, like why are these commas afterwards? These are all the calls of all the nodes all the way up to the top. The commas won't be printed out till we come back from the recursive calls. Because we're right here, it's going up, it's printing, then doing a recursive call and printing and not leaving. And so these commas are not printed until we come back. Like from right here. If I'd want to actually print out the commas, I'd have to add them in here. You can see, well now they're afterwards, but that's because it's before the actual recursive call would happen. So this is a very important thing to remember. So I'll just put everything back to the way it was supposed to be. Remove this code, make sure that this is all clean. Get back to our program here. So the very last one right here is, I won't go fully explaining this. We've done this before for duplicating an actual linked list. This was in a previous tutorial. But here we want to write a recursive function. So there is a solution for this already. Right here, the duplicate. But you just have to realize, go back to the original loop thing. Then we have again the loop list. But look here, what's happening is before the actual linked lists. Like what is it doing? It's duplicating as it goes up. So here's a case, we hit the end, don't go in here. If it's null, don't go in here. It's empty list, just have return null. So that's that temp, it'll return back null if we're at the end of the list. And so now here, it makes the new node, but this is before the recursive call. So it makes the new node, and then it's going to then, so it copies the data over from what you're working with right here, and then it waits to link till the next one. And so this will not be done till we return afterwards. So this next call here will go and duplicate another node and then return it. So it's kind of like going all the way to the end. So we make all these nodes and they're all waiting to be linked together, reaches the very end, comes all the way back, linking them all together. So again, before rushing off, like many of you may do, I do suggest please draw this out. Take an input. Just even take this create demo list 3 of what you'd have from the list and draw this out to make sure you're understanding the steps. And then see, how could you modify and play around with this? How could you change this code so it only duplicates every second node in the list? So that you could take an entire list and it's only every second node, and you come back a new linked list that has just every second node linked the list into there. Or every third node from right here. Like, how would you modify that code? But we're hitting at 35 minutes right here, and I'd still like you to have some time to play around with this code and change and get practicing, because I know that you may, one time of year when you're dealing with this, maybe earlier on, you have the midterms and stuff coming up, but you do have the next assignment, and you need to make sure you're understanding recursion. It takes a little more time, just like linked lists, to deal with. But if nothing else, wherever you are in life, whatever you're dealing with right now, like I like to end a lot of these previous videos with my little anecdotal things, is just remember to take care of yourself, and maybe also try to take care of the other people around you. Look at your fellow students and see if someone else needs help, just saying hi and asking for them and trying to connect to them. Maybe even reach out to your teachers, your tutorial instructors, everyone else, and just see how they're doing. We're all people. We all care in some way, and we're all dealing with our own kind of crap, and it'd be occasionally good just to maybe reach out and see, hey, are you doing good? Need to talk, whatever else, or not, or just to say hi and say, hey, I'm just thinking about you, and it'd be nice just to catch up or something. Who knows? If nothing else, continue being awesome. If you don't think you're awesome, as always, you are wrong, I am right, you are awesome, and have a great day.